Welcome friends. Today I am going to solve different types of problems of current electricity chapter. First of all, I am going to solve a problem with color code of resistance. A 200 ohm resistance has a certain color code. If one replaces the red color by green in the code, the new resistance will be 100 ohms, 400 ohms, 300 ohms or 500 ohms. First of all, we have to know the color code of resistance. In carbon resistance, like this, there are different colors in such way, same spacing. After that, one color more, it may be gold, it may be silver, or may not be there no color. It means if it is gold, then it indicates that tolerance plus minus 5% for gold. For silver, plus minus 10%. If there is no color, then we can consider the tolerance is plus minus 20% for no color. Now comes from those colors. First two colors represents number digit and the third one represent multiplier. For this example, it is a 200 ohm resistance. So we have to know B. Roy of Great Britain has a very good WH. It means white. So it is black, it is brown, it is red, it is orange, it is yellow, it is green, G for green, this B for blue, this V for violet, this G for grey, and this WH means white. And the figure for that color: black 0, brown 1, 2, 3, yellow 4, green 5, blue 6, violet 7, grey 8, and also white for 9. So for 200 ohms, it means 200 ohms, it means 20 into 10 to the power 1. So first two colors comes 2 for red. So the first color is red. 0 means black. Then the second color is black. And multiplier is 1 means brown. So the next color is brown. So the color of this resistance, having resistance 200 ohms, is red, black and brown. Now here the problem is, if one replaces the red color by green, if we replaces red by green, green means 5, so this becomes 5, so the resistance becomes 500 ohms. This is color code. First two color represents the number, it may be 1, 2, 3, 4, etc., etc. Third one represents multiplier. If the value is 5, then 10 to the power 5. If the value is 6, then 10 to the power 6. In such way, this is for 3 color carbon resistance. Now we can see that there are more resistances which has 4 color simultaneously, and the fifth color for tolerance. For those type of resistance, we have to calculate the first three becomes number and the fourth becomes multiplier, and those are numbers. Like if there is a resistance having color code black, brown, red, orange, the color code, from that color code value of the resistance becomes red means 2, black means 0, brown means 1, then 10 to the power orange means 3. This it comes to 0,000 ohms. It comes to 0,1 kilo ohms. So this is the color code. Now I am going to a second problem. Okay friends, now I am going to solve another problem using color code. The Wheatstone bridge shown in figure here get balanced when the carbon resistance is used as R1 has color code orange, red, brown. The resistance R2 and R4 are 80 ohms and 40 ohms respectively. Find the color code of carbon resistance used as R3. R1 has color code orange, red, brown. R2 and R4 are given 80 ohms and 40 ohms. We have to find out the resistance R3. Now in my previous problem I have already shown the color code. B.B. Roy of Great Britain has a very good white. This is brown, black, red, orange, yellow, green, blue, violet, grey, white, and stands for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So R1 has orange, red, brown. It means orange 3, value of R1 orange 3, red means 2 into 10 to the power brown means 1. It comes 320 ohms. Now if the Wheatstone bridge get balanced condition, we know the balanced condition of a Wheatstone bridge I have already discussed in my previous tutorial. You can see there, that is if P, Q, R, S, they are nearly equal for resistances, then the null point condition is Ig is equal to 0, galvanometer current is equal to 0, then P by Q is equal to R by S. This is the null point condition when galvanometer current is 0. So if the bridge is balanced, then we can find R1 by R2 is equal to R3 by R4. Hence R3 is equal to R1 into R4 by R2, and it comes R1 means 320 into R4 40 by 80. It comes 160 ohms. So value of R3 is 160 ohms. Okay, let's start with another problem. When the switch is in the circuit, here is a switch like this is. When the switch is in the circuit shown in closed, then the value of the current I will be 4 ampere, 3 ampere, 2 ampere and 5 ampere. If we watch this problem very carefully, then we must know the Kirchhoff's current law, which state that all the currents, sum of all the currents directed to a point means Kirchhoff's current law. It is a point, this current is coming I1, this current is coming I2, and this current is passing through, directed from that point away, that point A. Then Kirchhoff I1 plus I2 is equal to I3. The sum of all the currents directed to a point A is equal to sum of all the currents directed away from that point, away from the point A. So this is the Kirchhoff's current law. Now if we apply this in our circuit, if Vc the potential of that point, then here I1 plus I2 is equal to I3 from KCL. Now I1 means VA minus VC by 2 plus I2 VB minus VC by 4 VB minus VC by 4 is equal to I3. Here B is equal to 0 because it is connected to its ground, so the potential of the ground is 0. So VC minus V by, that is 2 ohm. Now if we put the value, be 20 minus VC by 2 plus 10 minus VC by 4 plus VC minus 0 by 2. If we calculate this, 40 minus 2 VC plus 10 minus VC, sorry, this is equal to 2 VC. If we calculate minus 3 minus 5 VC is equal to 50 minus 50. So VC is equal to 10 volt. If VC is equal to 10 volt, then the current I is equal to VC by 2. It comes 10 by 2, it comes 5 ampere. So the right option is D, 5 ampere. Okay friends, the another problem is, in a meter bridge experiment, the circuit diagram and corresponding table are given below. This is circuit for meter bridge and their data sheet, serial number 4 with serial number 4, and all these readings comes from this experiment. We have to find out which reading is inconsistent. Which reading is inconsistent. We have to find out. Now we must know the meter bridge condition, that is, if this is the point A and if the length is L, then rest is 100 minus L, because we must know this is a meter bridge, the length of the wire is 100 centimeter or 1 meter, and that's why this bridge is called a meter bridge. So if we put the jockey at that point and the bridge reach to null point condition, then this length, if this length is L, this must be 100 minus L, and in null point condition, as we say previous tutorial, that P by Q is equal to R by S. First of all, I am going to introduce which is P, which is Q, which is R, which is S. This is known resistance, this is R, this is unknown resistance, which is S, and the resistance of this wire is P, and the resistance of another part of the wire is Q. So this is P, this is Q, this is R, and this is S. So this forms a Wheatstone bridge, and we know at the null point condition, that is P by Q is equal to R by S, when Ig is equal to 0, no current flows with galvanometer. This is null point condition. Now I am going to illustrate all those readings separately. In serial number 1, this reading. So here we can find that S is equal to R into Q by P. It means R, Q means 100 minus L by L. If we consider P is L, this length is indicated by L. Now for first case, R is equal to 1000 ohms and L is equal to 60. So here S is equal to 1000 into 100 minus 60 by 60. It comes 667 ohm. Now case 2, by serial number 2, R is equal to 100 ohms and L is equal to 13. So S is equal to 100 into 100 minus 13 by 13. It comes 669. Now case 3. In this reading, R is equal to 10 ohms and L is equal to 1.5. So S is equal to 10 into 100 minus 1.5 by 1.5. It comes 665 ohm. And in case number 4, R is equal to 1 ohm and L is equal to 1.0 semi. Then S is equal to 1 into 100 minus 1 by 1. Here it comes 99 ohms. So if we illustrate all those readings, 667, case number 2 669, case number 3 665, almost they are nearly equal, but this is odd one. So this reading is inconsistent.